My team is engaged in next generation electronics, and in this case we're taking two semiconductors and at the nanoscale engineering them to produce a new type of transistor, a silicon-germanium transistor, which has two key pieces of functionality that don't presently exist. One, the ability to operate at very low temperatures, and two, the ability to operate unshielded in a radiation environment. Leveraging that, we can then redesign the way electronics is practiced in space. While it might not seem like it, the moon is actually a terrible place to be from a human perspective. If I'm in the sunlight, I'm at 120 degrees Celsius, but if I'm suddenly in the shadow, in the dark, now I'm at minus 180 degrees C below zero. And that freezes to death virtually anything you'd like to put there, including electronics. So if you look at the way that we went to the moon in the Apollo missions, we obviously put a rover up on there in the later Apollo missions. The way we did that, because there was no such thing as an electronics technology that would operate on the surface of the moon, we took a giant oven, literally, and buried all of the needed electronics inside that oven. And that's actually what's up on Mars now with the Mars rover. It's done exactly the same way. So that's sort of the business as usual model for NASA. Huge disadvantages in size, weight, power, and reliability. And what we proposed was to develop silicon-germanium technology as an electronics platform for doing out-of-the-warm box electronic systems. We had 6 university partners, 3 industry partners, and a wide number of collaborators. By the end of this 5-year program, we ended up using 82 students, graduate students. We demonstrated, A, that the technology could do what we said it did, and then importantly, we developed all of the infrastructure needed for anyone to do electronic design for these types of environments using what we developed. So some of the things that you would see in the lab downstairs would be specially designed cryogenic test systems that actually will take our electronics down to very low temperatures, in this case about a minus 180 degrees C, so very, very cold, and allow us then to electrically exercise them to show that they continue to function across the temperature range for which they're intended. NASA was on board from minute one. They were raved about the results at the end of the day. Some of our silicon-germanium components are up in Earth orbit right now, functioning on the International Space Station, just as a demonstration vehicle of what we want to do. So the next step will be to put this on a Mars mission or a Saturn mission or into some satellite system, whatever it would happen to go into. There's not a single space mission for exploration or discovery that would be done that wouldn't require this type of object in it. And that's actually kind of exciting, because what we've done from a science and engineering and demonstration perspective could ultimately find its way on all sorts of actual NASA missions.